Yeah, thank you for the introduction and thank you for inviting to this to giving a talk here. So definitely I graduated in Utah. So the first time I met Gordon is of course in Utah. So but I did not really have much interaction during my graduate study at that time. So and I remember that's the first time I have more interaction with Gordon is actually in a conference in Germany, so in 2016. So and at that time, so we start to discuss more on math and talk about some Whittaker model, Hecke algebra, and governed graph representation. So after this conference, we start to collaborate and write some papers together. So and this is the first two papers we wrote together and published. So and this is about something related to today's talk. And surely I learned a lot from Gordon. So and thank you very much. And my topic today is not quite related to minimal representation, but Gordon works on a lot of things. So one thing is about Hecke algebra, and one of his earlier work is about Hecke algebra on metapathetic groups. So okay, so I will start my talk now. So okay, so I will talk about the quotient branching law. So and Gn is GL and F. So and F is non-Archimedean. So I only consider the non-Archimedean case. So on Tuesday we have some talk by Professor Kobayashi and Professor Fraham. So for the Archimedean case, so, but I mainly consider non-Archimedean case today. So and we consider the branching problem. So we consider Gn as a subgroup of Gn plus 1. So through such embedding. So there is more than one embedment, just fixed one. So in the way stated here. So okay, so and Melissa told us the multiplicity at most 1 yesterday. So I will go through it quickly again. So if pi1 is an irreducible representation of Gn plus 1 and pi2 is an irreducible representation of Gn, then the dimension of the Hom space or pi2 appears in the quotient of pi1 at most 1 time. So this is what usually we call multiplicity at most 1. So and proved by Eisenberg, Gorups, Schipperman for non-Archimedean, and Sun and Zhu for Archimedean. So and the next question is, natural question is to determine when it is non-zero, when it is 1 or when it is 0. So I will give an answer almost the answer. But first I want to state and improve the result. So rather than consider irreducible one, we can consider the standard one. So in the sense of Lennon's means that every irreducible representation appears in certain standard representation. And then in such ways, the Hom space here has dimension 1. So the dimension of the lambda 1 and lambda 2 check means the dual, the smooth dual representation. So, and the higher H group is always vanished. So those H groups is conjectured by or studied by Bernstein-Zelevinsky. So and he also gave some related talk on Monday. So but in the Theta Correspondence, of course, he also mentioned those branching law before. So okay, so and let me review some previous results. So and the most classical one is the generic ones, or sometimes we will call Gan-Gross-Prasad conjecture. So but of course it is known by Hecke, Bernstein-Zelevinsky, Shapiro, Hecke in 1983. And Bernstein-Prasad study about the distinguished case, which means that pi2 is trivial representation. So and pi1 is arbitrary. So or power arbitrary Gn plus 1 representation. So and Bernstein proved that for when n equal to 2. So his students when Brahmanian, so proved that for general n. So and John with Gordon. So we also study a kind of opposite case. So pi1 is some kind most generic one, you can say. So generalized stable representation, and pi2 is arbitrary. So basically we determine the quotient brancher in such case. And also Gan-Gross-Prasad have a recent conjecture. We heard it in several talks before, Bayern, Dihua, etc. So So I completed the proof, and Max Guravich has some important work in before. So okay, so okay, so I will talk about a quotient branching law later. But I want to mention an important tool. So there is the Bernstein-Zelevinsky theory, and in particular the derivative. And this is based on my recent preprint on the archive. So and I updated it 2 days ago. Or in the weekend. Okay, so let us review the definition. So, Ri is unipolar matrices containing those matrices of the forms. Also, In is the identity matrix. U is some kind of upper triangular matrices, and reflect some non-degenerate characters on UI. So you have the upper triangular ones. So and you sum up those subdiagonal entries U1, 2 plus up to UN-1 n. And side bar is some kind of non-trivial character here. And then just extend trivial to those Ri. So there is no transfer here. So I put it on here. Okay, so just Ri to here. So and then we consider those twisted Kei bundles, something similar to Professor Gan talked about yesterday. So then we consider the maximum quotient, or acting on it. So and we call it I Bernstein-Zelevinsky derivative. Okay, so okay, so this is the definition. So the kind of twisted Kei bundle. If the original Kei bundle we don't have the side I, but we add some character on it. Okay, so let's review some main properties that mainly due to Bernstein-Zelevinsky, Garfin, Castan, etc. So those funda is exact funda, and preserve the finite length. And so because it is finite length, so you can talk about the SOGO and co-SOGO. So for irreducible ones. So here the SOGO pi is irreducible for the third point. So for the pi irreducible, the SOGO and co-SOGO are multiplicity free, and this is basically those multiplicity one theorem consequence. And with some Bernstein-Zelevinsky theory. And also the SOGO and co-SOGO are isomorphic. So that means you just study one of its either SOGO or co-SOGO. So then you will get one from another. Okay, so this is some properties of Bernstein-Zelevinsky derivatives. So there are some calculations. So then the next question is to talk about what's the Bernstein-Zelevinsky derivative looks like. So let's consider the level. Level is the largest integer, so makes the pi I is non-zero. Then if I is the level, so then the highest derivative is irreducible. So this is a theorem by Zelevinsky, so non-trivial theorem. And in some sense, you can, because it is irreducible, you can repeat the process. So then you will get a partition. So basically, such partition is the Raven says is similar to the Emily Oka talk about yesterday. The GLN case, getting a partition. Also some similar idea to the Professor Jan talked about yesterday. So then there are more some explicit descriptions. So for example, the square-integrable case is known by Zelevinsky in his originally defined those derivative things, so 1980s also. And then in more recent work by Lapin, Mínguez, and determine the derivative for the later representations, including those unitary one-state representations. And this is earlier conjectured by p-adic, so in 1987, so around that time. And one can also define rather than using the Ri, so you can take the transpose, so some kind of opposite unipotent. So you take the opposite unipotent, then you can define the left Bernstein-Zelevinsky derivative. Then there are some interesting property that is called asymmetric property. So it means you don't have common isomorphic simple quotient. So when it is not the level, but I won't talk to do that there. So then why is Bernstein-Zelevinsky derivative important in branching law? So I will just give a short answer here. So the short answer here is that there is some kind called Bernstein-Zelevinsky filtration. So once you use such filtration, so you turn the branching problem, the Horn space, non-zero at the left, the home pi1, pi2 non-zero. Then after the precision, you pick one of the layer. Then using some adjoint species, then you can change the home to the another form, the home GNI, and then with some twisting loop, half so pi1 I, and then and then some kind of that is the left derivative. So we introduced in the first page. Here nu is the determinant characters, which is by some characters. And also the topic today is about Hecke algebra. And so the relation is on some categorical business. Also, depending on how much time we have at the end, we'll talk about the Hecke algebra at the end. So let's first of all, we will talk about more on the derivative. So we introduced the notion of another derivative. This is not the same as Bernstein-Zelevinsky derivative, but it's useful in the combination. So for that reason, I have to record the classification of the essentially square-integrable representation. So, and those could be classified by something called segments, some combinatorial data. So the segments contain three things, so A, B, and rho. So A, B are integers, and B minus A the difference has to be non-negative. So and rho is some kind of hospital. So we usually think about the segment as a set. So in such forms, a set of containing some cuspidal representation, no A rho, no A plus rho, etc. So it's a set. So it is important because later on we will do some intersection unions. So we really have to know it is a set. Okay, so then basically Zelevinsky said that those essentially square-integrable representations can be classified by those segments. And we can do explicit construction. So construction is you do the products. So the product means the parabolic induction. And you parabolic in those GM something, and then go to some larger group is Gn, n is something like b minus a plus 1 times n, so something like that. So you do some parabolic induction, and then you pick the irreducible quotient one, that is something we call generalized stable representation. Okay, so then we need this thing. So okay, then we need to do derivative. So then the basic result is to have this theorem. So let's see what it says. So net stable delta in essentially square-integrable representation of GR for some R. So and then there is at most one optimal isomorphism tau, so in the irreducible representation of Gn minus 1, such that as Gn minus R times GR module, so the tau tensor with stable delta, so can be embedded to the pi nr. So pi nr is Kei module. You pick suitable unipolar radical and then take the Kei module. Then that gives you the pi nr. And then there is at most one tau there. So this is result for delta equal to rho is due to Jantzen and Mínguez independencies, and then for more general result is the p Mínguez. Okay, so then if such tau is exists, then we will just denote it by d delta price also. And we say it to be zero if it is it does not exist. Okay, just some terminology also. And we just mentioned there are some interesting directions. So try to generalize those square-integral representation, or even more later representation, something to the square-integrable representation. So there are some recent papers by Mínguez doing such things. Okay, but we won't use those things in this talk. So okay, so and also mention some other application work, and we consider those things branching law, something. So there are some theta correspondence. This is the only place the theta correspondence appears in my talk. So by Mínguez, Gan, Takeda, and also other applications contain the about Zelevinsky duos, Gan-Gross-Prasad, Adobe, Mínguez, and then other package goes through Adobe, and then also on the Monday talks by New and their students. So, okay.
Can I just make a small comment?
Sure.
Just for the record, the result that you mentioned that it's due to me and Mínguez is actually a transcription of result of Kang, Kashiwara, Kim, and O.
Okay. Yeah, maybe I should mention the result, the KKKO results in the quantum affine Hecke algebra setting. Okay, thank you very much. Yeah. Okay, so okay, so now we will try to compute those derivative things. So but we will need to arrange in certain ordering. So just like you do the standard module, you need to do some ordering to make the standard module good enough to have the unique quotient. So then just consider the multi-segment. So multi-segment means a collection of segments, but each segment can appear more than one time. So then we arrange in ascending order. So just for simple, so that means your integers values is a1 less than equal to a2 and so on up to ar. So okay, so then for the D multi-segment M, sorry, so here should be M. So M here, so pi, then there is a sequence of derivatives d delta 1 up to d delta r. So in the fixed ordering. So okay, so of course there may be more than one ascending order, but you can prove that it is independent of such ordering. So just some formal basis to prove it. And one thing is related to Bernstein-Zelevinsky derivative. So this is our main focus today. So this is that yes, such thing is a simple quotient of pi I. So of course, if this is non-zero, if this is zero, then there is nothing to say. If this is non-zero, then when we arrange in such way and then do the derivative, then there is a simple quotient of
Are you still here? It seems like we missed the speaker, lost him.
sorry, so this is so I cannot share the screen now. So this is the problem if I stay at home, the internet always open. So I cannot share the screen now. So do you hear me? I cannot share the screen now. So could someone enable me to share the screen?
Yeah, 1 second, Kane. We are trying to find out how to make you a co-host again.
Okay, sorry. Okay, yeah, I could share now. So So I think everyone see it now, right? So I think I stop here, right? So and so let me continue to explain this proposition. So okay, so basically you do the consequence of a sequence of derivatives, then you will get a simple quotient. And basically, so and the idea of proof is using some Jacobian. So maybe I won't go through quickly. Just go through quickly. So and one key thing is that you only have a unique simple quotient in such form. So it is a kind of dual of standard module. So it's generic. So it is related to those so-called injectivity conjecture of correspondence. Of course, in GL case, it's much simpler. Okay, so. All right, so and then now the next question is we try to understand these sets. So if we consider pi is irreducible representation and tau is some kind of simple quotient, so define S pi tau so is which multi-segment will give the simple quotient. So we can such sets. So then the question is we want to study it. So then ask about the combinatorial structure, and the another question is it non-empty also. Okay, so I will talk about the combinatorial structure first. So then what do we mean by combinatorial structure? So we define some combinatorics on it. So then a multi-segment M is obtained from another segment N by something called intersection union operation. It also appears in Bernstein-Zelevinsky. So and if there is a pair of length segments, delta 1, delta 2, so such that if you replace the delta 1, delta 2, the segments in N by those intersection and union, so then we get the M. So in such case, so we call it is obtained by one intersection union. So and if we do it a sequence, then we will give the ordering that the M is smaller than or equal to N. So the first two main combinatorial property is the following. So the first one is that a kind of closest property, so which means that if you have two multi-segments S pi tau, so with M is less than or equal to N, so then any N pi which appears between M and N, so under the such ordering, then you must also inside such sets. So this is the first property. So the second property is uniqueness property. This is important, so I will explain later. And if this is non-empty, so we have not discussed empty or not. So just assume this is non-empty right now. So if this is non-empty, then it has a unique minimal element. So in such a way. So and just make a remark. The maximal one is not true in general. So and you can also compute the minimal in some special case like generic representation. Then in such case, those multi-segment has to be or mutually unlinked, something like that. So we can also have another special case. So that is the highest derivative we mentioned in quite beginning. And okay, so then to have explicit description, so let's introduce more notation. So M is another multi-segment, so we call it multi-segment at a point C. So if any segments delta M takes such form, so C B rho, so for some B, so okay, yeah, C is fixed and B is any. So basically, if you do the Lennon's quotient, is one of the generic representations, but yeah, more specific forms. So okay, so and then property is that there is only unique maximum multi-segment and at the point, so such that which is the derivative is on. So it is possibly empty. So if there does not, I mean, you can choose it to be empty one. So yes, okay. And the maximum one is a kind of you sum up all the lengths at the largest one, so some kind of that's okay. And the highest derivative multisegment is defined as follows. So you sum up you union all the multisegments at the one point, but there is only finitely many non-empty. So basically, if you sum up all the things, you still get only a finite number of segments. So okay, and okay, so then this will give you the description. The highest derivative multisegment gives you the description of the minimal element in this special case. So S pi minus. So pi minus means the highest derivative, which is the highest derivative I star. So I star Bernstein-Zelevinsky derivative. So as we say that before, it is irreducible. So this notation makes sense. So, okay, so hopefully this gives you a good example of the minimality. So basically, that should be some representation theoretic interpretation, but I have not really proved such thing, but I think it should be true. So yes, some kind of that. If you do those sequence of derivatives, this is in ascending order. So just as before, so in ascending order. So then you can have a non-zero map. As such, non-zero map is unique. Unique business is a kind of similar to the unique business in those so-called and co-so-called things we talk about. So the map is unique. So non-zero is followed by those Frobenius response K-module business. So the conjecture is that if those sequences in minimal ordering, so then the non-zero map should be injection. So not just non-zero, it has to be in zero, totally embedded to its block. Okay, so basically, so this gives you some structure on those representations, I think. So, okay. And there are also some interesting properties also, and yeah, so let's see. So the first thing is the subsequent properties. So what does it mean? So we choose pi to be irreducible representation, and n is the minimal one. One of the minimal one means that you do when you consider the set S pi and then Dn pi, the n has to be minimal itself. So in the previous sense, so then any sub multi-segments n pi so is still minimal to pi. So actually, it's quite strong. So because it also says that when you do the sequence of derivative, it is non-zero. So it is not true if you pick non-minimal one, non-true in general. If you pick the non-minimal one, but minimal one, you have some good properties also. Another one is the commutative and the properties. So and when we choose pi to be irreducible, I want again, so n is multi-segment, so minimal again. So if we remove any one of segments, so in n, so then we rearrange the ordering. So then you this can be any, can be the last one or in the middle one. And then you rearrange the ordering. So they have to be then isomorphic. These two derivatives. So and moreover, so n minus delta is minimal to such d delta pi. So, and the special case is when n just two linked segments, so it means you can do the intersection union process. Then it means when you arrange in the ascending order, so delta 1, delta 2 means you arrange in ascending order. Then if you do the intersection and union process, it does not the same. So then basically it says that is minimal because this is another one that the only possible chance to make it non-minimal. So if this is non-isomorphic, so and then that means these two segments are not in those sets S pi with the corresponding derivative. Then they have to be commutative. So okay, it's a kind of commutative result. Okay, so and then okay, so we talk about a lot of the minimal properties. So then how do we get those properties? So basically our strategy to get is to transferring everything to the combinatorics. So we only talk about the intersection union process, but we need more combinatorics. So now we introduce epsilon invariant. So, okay, so what does it mean by epsilon invariant? So, we choose a segment delta AB rho, so and irreducible representation pi. So epsilon delta pi is the largest non-negative integer to such that the sequence of derivative make it the largest integer k, I put k here, the largest integer k to make it non-zero. So, basically, the highest derivative multisegment contains all the information of this epsilon delta. So, although I defined it a little bit in different ways, so using the uniqueness of mathematics, but I mean, those mathematics is quite the same as the mathematics, the largest integers here. So that's why such two notions agree. So, okay, so then basically, so the highest derivative multisegment record those information. So, and to do such things, so we define another multisegment, and it is quite combinatorial algorithmic. So I want to talk the detail here. So, but this basically such R delta pi. So the main point is to keep record the change of the highest derivative multisegment. So, what do I mean by keep record the change? So I make it precise in the next page. So and first of all, we define it for a sequence. So for n a multisegment again, so we define for sequence. So then that means you do the such R process. So I call it removal process. So several times, so from delta 1 to delta R, and then so the meaning of you keep records the change of derivative is in the following theorem. So if we have two derivatives which give you two multisegments, give you the same derivative on pi, so then they have the R process, the multisegment obtained from the R process has to be the same, and the converse is also true. So that basically saying that the R keeps record a lot of the information of those derivative on multisegment. So and the property is important. This is a double derivative result. So basically, it says that if you have n multisegments, so then it gives you a non-zero derivative. Then you first do the derivative on n, but then you can do the remaining ones, so the R process after the R process one, and then you do it twice. Then you will get the highest derivative. So yeah, so this is a kind of interesting property. Also, and yeah, also useful. So, okay, so I keep going. So okay, so now let me see. So we almost go to the branching law, right? So we need some other finite invariant. So we basically talked about the epsilon invariant before. So now we talk about the eta invariant. So basically it's a collection of epsilon invariants. So you consider more than one segment. So you cut the length each time by one. So AB and A minus B, A minus 1 until there is only 1 point, one singleton B growth. So pi. So here. So okay. So and this invariant is important. Why is it important? Because of the following key properties. So it's a kind of generalization of the case of when delta is low, obtained by Jantzen Mínguez for p-adic groups and Gan-Gross-Prasad for Bernstein-Zelevinsky for the affine Hecke algebra case. So and it says that if you consider the n the multisegment, so also those segments from AB and up to B, and then with suitable multiplicity, keeping occurred by the epsilon invariant. So then such segments, you will appear in pi n. So of course this is an injection, but this statement says that it is stronger than just injection. Injection we have explained before. It is a direct summons also. So basically it is a quotient and submodule. So okay, so yeah, so when as I said before, so, the singleton case is before, and also And also you need a collection of it. If this is not a collection, this is also not quite true. Okay, but we want to do branching law. So we will go back to the eta invariance soon. So we want to do branching law. So we need to do the integral. So also the kind of inverse process of derivative. So then if we keep record of the such a notation pi is irreducible representation segment delta. So then we call I delta pi. So I will put L here because I will put Steiber delta on the left here. So you can put on the right. If you put on the right, then you put out here there. So I will sometimes put L here. So then that means what does this module mean? It means this is a unique submodule of this parabolic induction. So this is also some results of by Kei Yuen Chan, Mínguez, and etc. So yeah, and so as I say, this is a Kafka inverse because if you do the integral one time and then you do the derivative one time, so this is isomorphic to itself. So if you change the ordering a little bit, D first and I first, you need to be careful if this is non-zero or not. So, but, okay. Kind of inverse. So okay, so now we put two notations together so to define a new notation. So pi is irreducible representation. So delta 1, delta 2 are two segments. So then we consider a triple. So a triple delta 1, delta 2 pi. So just I call it combinatorial, right derivative, left integral combinatorial triple. So try to keep all the information here. So right derivative means what do it means? Because we do an eta invariant here. Eta invariant, recall that we are doing on the right. So the original right derivative. For the integral, we are doing on the left. So I emphasize L here. So, okay. And if such invariant, they are the same. So then I call it such terminologies also. Okay. And why do I use commutative? So commutative means because of the following result. So I think it is not quite true because I take some time to prove it. So if delta 1, delta 2 pi, so is a combinatorially, so RDLI commutative triple, then it is really commutative in such sense. When you do the derivative first and then do the integral, so yes, I'll move it to the derivative integral first. So the proof is a kind of using Bernstein filtration. So those geometric lemmas, using geometric lemmas. So but you have to keep track some information there. So because you use geometric lemma, you can also replace this definition in terms of parabolic induction. That this definition is convenient in some computation. So, okay, so I will just mention this definition here. So, okay, so and now we consider a sequence. So here we just do a one segment. So we consider a sequence here. So then M is in ascending order, so delta 1 up to delta R, and also in ascending order. But one is for derivative, the other one is for integral. So then basically, so if you're doing the multi-segment case, so Mn pi is called strongly RDLI commutative triple. So then we call, then if you're doing, you do different subsequence or just part of it, then you add term by term, then such thing is still has to be combinatorial RDLI commutative triple. So I call it strongly because of the previous result. The previous result saying that this is commutative, but in general, it is not, the converse is not true. So that's why I call strongly. So strongly means you just have one direction for the commutative. So Okay, so this improved from from segment case to multi-segment case. So okay, so so now we go to how to define the relevant pair. So for the branching law, the way to define it is the following. So pi and pi irreducible represent of Gn are not necessarily corank ones, because we know that for the Gan-Gross-Prasad those conjectures, you can also doing Bessel model things. So corank can be higher than 1. So and pi prime, so it's relevant if there exists multisegment M and N, so such that making MN null half pi is strongly RDL commutative triple. And then if you're doing those derivative thing, you can get to the pi prime. Well, so if you are familiar with Bernstein-Zelevinsky filtration thing, so you may think about that the DRM is doing the right derivative, and then you doing induction. So of course it's still right, but because of the quotient submodule business, you have to do it left here. So and this is basically checking the information of the Bernstein-Zelevinsky layer. So and then you have to be in such way. So and basically the Gan-Gross-Prasad have defined some relevant notions for the alpha type representation for the result is for all classical groups also. And such two notions to be the same. I did not really check everything, so but one direction is easier. So I did not check combinatorially everything. So if we are assuming the Gan-Gross-Prasad relevant for the alpha type representation, then it is relevant for in the sense I introduced above. So then you may wonder that can we, because for the Bernstein-Zelevinsky fusion, we have two forms. One is doing on the right, the other is doing the transpose one. So I talk about the transpose things. So then there is no transpose things here, but actually this is automatic. So if you have pi relevant, then if you switch it, then that is also relevance. Then basically you keep checking. You explain why the left and right branching laws business does not really matter in our notions. Okay. So then that is to say the quotient branching law. So basically is say that the terminology determines the branching law. If pi and pi prime, so are irreducible representation, then it's relevant in the sense I introduced it in the previous page. Then the home space is non-zero. So basically, I completed the proof, but the proof is slightly long. So yeah. So just let us see the consequence also. So so if we consider derivative things, so now we try to go back to the simple quotient derivative things. So then we consider tau is some simple quotient of some I. So then we consider the irreducible representation of tau cos sigma. So for some hospital to make it irreducible, then we can make it this to appear in the quotient. So then basically, if we have the theorem A, so then pi and tau cos sigma has to be relevant. Then because we know that the relevance is defined by those derivative things. So from there, one can obtain that if tau is irreducible simple quotient, then there exists multisegment such that the n pi isomorphic to tau. It's basically solved the long empty problem before. So yeah, but in reality, so actually we need theorem B to prove theorem A. So the proof there is a kind of interaction between those things, also using those left and right spaces to make it work. So far the proof I got is there. So, okay, so. All right, so I don't have much time left. I will go through the alpha Hecke algebra things quickly. So basically, alpha Hecke algebra is those defined by some generators, so theta 1 and theta n to 1 to the end to satisfy some relations. And the two important things is one is commutative subalgebra, and other thing is a finite Hecke algebra. So, and basically join with Gordon, so we defined the Bernstein-Zelevinsky derivative. So basically we create sign representation. So this is a kind of alternating sum of those generated in TSI, so those finite TTI things. Okay, and we define the Bernstein-Zelevinsky derivative as by using this. This is a kind of some operator in the Hecke algebra and acting on it. So then you got a submodule. So and because the HNI minus parts commute with HI parts, so then you get a submodule HNI minus module. So basically this sets up the quotient branching problem. So in a higher branching problem, so I can bigger than one. And as the home space as before. So okay, so when I go to one, this is a classical result of Gorups and Bernstein, and also related to those both derivative things. And so, but how do we solve the alpha Hecke algebra problem? So the way is using the general linear group we proved up just before. Basically, we have the categorical equivalence for the UR restricted points or HK module. So this is very interesting alpha algebra business, because you can transfer information between those things, and some work by Albert Babbage, Chibalawa, and Herman, Autumn, with Moy and Gordon. And of course, but most of the time they try to transfer the information of Hecke algebra to p-adic. So because Hecke algebra has some good structure, so we have some explicit structure like commutative algebra, but Hecke algebra. So but we can also turn the table around. So is what we are doing here. So trying to use branching law to go to Hecke algebra branching law. So as I mentioned that the branching law in the p-adic group is not quite the same as the alpha Hecke algebra. It is related, so of course, because we try to transfer the information. And also that this is my last page. So basically under the such equivalence drawn with Gordon, we prove that the derivative correspond to the Bernstein-Zelevinsky derivative. So then we can now transfer the information. So for example, we can use the multiplicative free. So to prove that the Sobo and Kosovo are multiplicative free. So again, this is the p-adic group doesn't use the results of the AGRS. And of course, this also solves the exclusion problems and in such a sense. So okay, I will stop here. So sorry for that. So thank you very much and happy birthday to Gordon. So.